Hi, it's a pleasure to be able to speak again at the National Forensic College summer meeting. I apologise that I can't, for family reasons, deliver this talk live, but at least that means you've missed all the mistakes I've edited out. Before I start, I want to make clear that despite the fact that I've often been used as an expert to critique the use of likelihood ratios in prosecution forensic evidence, this doesn't mean that I'm opposed to this kind of evidence. On the contrary, I believe that when used properly in the context of Bayesian reasoning, likelihood ratios and Bayes provide a natural and extremely powerful method for both evaluating the strength of all types of evidence and for presenting such evidence. However, the problem is that most uses of the likelihood ratio in practice are fundamentally flawed in a way that abuses Bayes' theorem and the logical conclusions that you can make. So I'm going to start with a reminder of what the likelihood ratio actually is. I'll highlight the genuine confusion about the likelihood ratio and Bayes' theorem, and this includes not just misunderstandings about the role of the so-called prior probability, but also why even many so-called statistical forensic experts fundamentally misunderstand what can be done with the likelihood ratio. Indeed, I'll show why most uses of the likelihood ratio in forensic evidence, especially DNA evidence, are fundamentally flawed and incorrect. Now, in the absence of any other evidence, it follows that there are solid, albeit poorly understood, mathematical reasons why most uses of the likelihood ratio in DNA evidence, especially mixed profile evidence, can and should be dismissed. However, in practice, these fundamental flaws and errors might not help the defence case. And that's because the lack of a prior probability is not as big an obstacle as is often claimed. In fact, the existence of what we call the opportunity prior can mean that even erroneous DNA evidence can be highly probative against the defence. To explain what the likelihood ratio is, I'll use a topical but non-DNA example. Imagine that we've got an accurate test for whether a person has the SARS-CoV-2 virus. Now let's assume that there's a 0.1% false negative rate. So for every 1,000 people with the virus, there'll be only one who wrongly tests negative, but 999 out of the 1,000 will correctly test positive. And let's assume that there's a 1% false positive rate. So for every 100 people without the virus, there'll be only one who wrongly tests positive. 99 will correctly test negative. We discover that Sarah tests positive. What does this evidence tell us about the probability that she has the virus? Well, the likelihood ratio is a measure of how probative a piece of evidence is in support of an unknown hypothesis H. So in this case, the hypothesis H is a person has the virus, and the evidence E is the observation that the person tests positive. Now, because we know the test accuracy, we know the probability of a positive test given the person has the virus is 0.999, i.e. 99.9%, because that was the false negative rate. And the probability of getting a positive test result if the person doesn't have the virus is 1%, 0.01. The likelihood ratio is simply defined as the probability of E given H, which we know is 0.999, over the probability of E given not H, which is 0.01. And so the likelihood ratio is 99.9. And this means we're nearly 100 times more likely to see a positive test result in a person who has the virus compared to a person who doesn't have the virus. But what does this actually tell us about the probability the person has the virus? Now, many people wrongly assume that the probability the person has the virus must be something like 99.9%. But that's the probability of a person with the virus testing positive, i.e. the probability of E given H. We need to know the probability of H given E, which is called the posterior probability of H, i.e. the probability of H once we know they test positive. To assume the posterior probability of H is the same, i.e. 99%, as the probability of E given H, is the so-called prosecutor's fallacy, or fallacy of the transposed conditional, because we're assuming the probability of H given E is the same as the probability of E given H. In fact, we need to know the prior probability of H in order to use the likelihood ratio to determine the posterior probability of H. And Bayes' theorem tells us how to calculate the posterior probability of H from the likelihood ratio. I'm going to give a graphical explanation of Bayes' theorem. Suppose that the prior, which is the population infection rate, is 1 in 1,000. Imagine that you've got 10,000 people randomly tested. Then about 10 of those genuinely has the virus. But because of the 1% false positive rate, about 100 of the remaining 9,990 who don't have the virus will test positive. Now, we can assume that the 10 who really do have the virus test positive because there's a very, very low false negative rate. So that means that out of the 110 in total who test positive, only 10 actually have the virus. So if you test positive, there's actually a less than 10% chance that you have the virus, meaning the vast majority of people testing positive are false positives. The so-called odds version of Bayes' theorem states simply that the posterior odds of H are the prior odds times the likelihood ratio. So in our COVID example, the prior probability a person has the virus was 1 in 1,000, which means odds of 999 to 1 against having the virus. We know the likelihood ratio is 99.9, so when you multiply those together, you get the posterior odds of 10 to 1 against having the virus, which is a probability of 1 in 11, as we demonstrated graphically. Moving to DNA evidence likelihood ratios, let's consider the case where a single DNA profile is found at the crime scene. Then after electropherogram analysis, the expert might determine that the alleles found on these loci are the ones stated here. So on the first loci we have 2 different alleles, 15 and 16, meaning the genotype is heterozygous, whereas on the second loci the alleles are the same, meaning it's homozygous. We then find the suspect whose DNA, when analysed, is determined to have alleles which are the same on each of the identified loci. The forensic expert declares this to be a match. So suppose H is the prosecution hypothesis that the crime scene DNA comes from the suspect. Then we can calculate the likelihood ratio of the DNA evidence in respect of H as the probability of getting that DNA evidence, given that it comes from the suspect, divided by the probability of having that evidence if it doesn't come from the suspect. Now the numerator here, the probability of E given H, is assumed to be 1 because if the DNA comes from the suspect, then we would, assuming no errors in the process, find exactly those alleles. The probability of E given not H is an estimate of the probability that a person other than the suspect would have exactly the same alleles on those loci. Now, all kinds of assumptions are involved in this estimate, which is based on the population frequency of the particular genotypes at those loci. So if on average each genotype occurs in 1 in 10 people, then a so-called unrelated person will have a probability 1 over 10 times 1 over 10 times 1 over 10, which is 1 over 1,000, of having profile. And that's a likelihood ratio of 1,000. Now, in the absence of any other evidence against the suspect, it could be argued that the prior probability is something like 1 over the world population, which could be something like 1 over 10 billion. In that case, the likelihood ratio only shifts the odds from 1 in 10 billion to 1 in 10 million. But if, as is typical, we find a match of 14 loci, then the likelihood ratio is approximately 10 to the power 14. And in that case, even with the 1 in 10 billion prior assumption, the posterior odds strongly favour H. Now, superficially, the use of likelihood ratios for mixed DNA evidence appears to be the same, but there are actually fundamental differences not widely understood, which means you can't make similar conclusions to a single profile case. So in this example, the crime scene sample is clearly a mixed profile because it's got more than 2 alleles at some loci. Now, for simplicity, let's assume that there are exactly 2 contributors. And let's suppose that we find the suspect's DNA profile is this. Then, as before, experts declare a match in the sense that the suspect is included on every loci. And again, now suppose the prosecution hypothesis of the suspect is included in the mixture, then we can calculate the likelihood ratio of the DNA evidence in respect of H as the probability of E given H again over the probability of E given not H. Now in this case, the probability of E given H is definitely not 1. It's the probability that the other person in the mixture will have genotype 1414 on this locus, 1618 on this locus, and 1012 on this locus. And again, if on average each genotype occurs in 1 in 10 people, then a so-called unrelated person will have a probability 1 over 10 times 1 over 10 times 1 over 10, which is 1 over 1,000. So in contrast to the previous example, the probability of E given H is typically a very small number, it's not 1. But E given not H is much smaller still, because this time we're estimating the probability that we would get these exact alleles in a combination of 2 people by chance. And again, assuming each genotype occurs in about 1 in 10 people, then getting that particular genotype combination at each locus is about 1 in 100, so the probability of E given not H is about 1 over 100 times 1 over 100 times 1 over 100, which is 1 in a million. And that gives us a likelihood ratio again of about 1,000, similar to the single profile case. So if we find a match on 14 loci, then the likelihood ratio is approximately 10 to the power 14. But unlike the single profile case, this does not provide overwhelming support for H. Well, let's look at possible DNA mixture profiles that match the crime scene sample. This combination is one in which the suspect's DNA is certainly included. But look at these other equally likely combinations. They all exclude the suspect's DNA profile. Now, theoretically, all of these are equally as likely as the first. And so, irrespective of the likelihood ratio, the posterior probability that a suspect is in the mixture must be very low. Now, this is the kind of argument that's explained in detail in this paper which I presented last year. But what is the fundamental confusion over the likelihood ratio and Bayes theorem? In a UK murder case called RVT, in which the likelihood ratio for footwear matching evidence was used against the suspect, the appeal court judgment included this very damaging statement regarding the use of Bayes for non-DNA forensic evidence. Now, as I said at the beginning, I don't agree with this statement, although I can understand why in this particular case the judge was unhappy with the way the evidence was presented. Now, there were many excellent responses challenging the judgment by scholars of legal evidence and forensics, including this one by Aitken and many other signatories. But it contained this very curious statement, which is even more damaging and confusing than the judgment itself. It is regrettable that the judgment confuses the Bayesian approach with the use of Bayes' theorem. The Bayesian approach does not necessarily involve the use of Bayes' theorem. Now, this statement's pretty bizarre, but what it was actually referring to when it spoke about the Bayesian approach was the likelihood ratio, suggesting that its use was somehow okay, independent of Bayes' theorem. But this statement reveals an astonishing misunderstanding of Bayes' theorem and the likelihood ratio, and it's the kind of misunderstanding in practice that totally devalues the use of the likelihood ratio. Now, as we saw, the odds version of Bayes' theorem provides the relationship between the prior odds, the likelihood ratio, and the posterior odds. And what this means is that it's because of Bayes' theorem, and only because of Bayes' theorem, that the likelihood ratio can be considered meaningfully to be a measure of probative value of evidence. And that's because a likelihood ratio greater than 1 means that the evidence supports the prosecution hypothesis, as the posterior odds in favour of H increase in this case. And the higher the likelihood ratio, the higher the posterior odds in favour of H. A likelihood ratio of less than 1 means that E supports the defence hypothesis, because the posterior odds in favour of H decrease in this case, and the closer the likelihood ratio is to 0, the lower the posterior odds in favour of H. And a likelihood ratio equal to 1 means that E has no probative value, because the posterior odds in favour of H are unchanged in this case. Now, before looking at the ramifications of that and what the serious misunderstandings are with the likelihood ratio, it's worth noting that when used properly, its benefits are that it is a simple formula for probative value of evidence. There really is no need to explicitly consider the prior for H in determining the probative value of the evidence. And it forces experts to consider the likelihood of both the prosecution hypothesis and the defence hypothesis, which also helps avoid the prosecutor's fallacy. But the problem is none of these are exactly what they seem in practice. The first issue is that how we interpret the likelihood ratio still depends heavily on the prior probability. So imagine that we have a single profile DNA match evidence with a likelihood ratio of 1,000, so something like a 3 loci match. Then if the prior odds were 10,000 to 1 against the DNA being from the suspect, the likelihood ratio of 1,000 means that the posterior odds are 10 to 1 against the DNA being from the suspect. And so it's still strongly against the prosecution hypothesis. But if, for example, the suspect was known to be one of only 11 people who could have been at the scene, then the prior odds are 10 to 1 in this case. And so with the same likelihood ratio, the posterior odds are 100 to 1 in favour of the prosecution hypothesis. And so the likelihood ratio is the same, but different priors for H produce opposite outcomes. Even more crucially, but generally ignored, if the prosecution and defence hypotheses are not mutually exclusive and exhaustive, meaning that the defence hypothesis has to be exactly the negation of the prosecution hypothesis, then the likelihood ratio tells us literally nothing at all about the posterior probability of the prosecution hypothesis. In such cases, no matter how big or small the likelihood ratio is, it's essentially useless. It is not a measure of probative value of the evidence. It tells you how the posterior probability of the prosecution hypothesis changes relative to the defence hypothesis, but it doesn't tell you anything about how the probability of the prosecution hypothesis changes generally. Indeed, if these hypotheses are not mutually exclusive and exhaustive, it's possible that you can have a likelihood ratio greater than 1, but the evidence supports the defence hypothesis, i.e. the exact opposite of what it's supposed to do. And you can have a likelihood ratio equal to 1, but the evidence can still be highly probative. And if you don't believe this, and many people find this hard to believe, then I've constructed some very simple examples which demonstrate the point. So first of all, a case where the likelihood ratio is greater than 1, but because the hypotheses aren't exhaustive, the evidence actually supports the defence hypothesis. I'm going to base it on a simple lottery. A lottery has 10 tickets numbered 1 to 10. Fred buys 3 tickets and gets the numbers 3, 4 and 5, and Jane buys 2 tickets and gets the numbers 1 and 6. The winning ticket is drawn, but it's blown away in the wind. However, a totally reliable eyewitness asserts that the winning ticket was a number between 4 and 10. Fred claims that he must have won and sues the organisers. The prosecution hypothesis, H of F, we'll call that, is that Fred won the raffle, which means that the winning ticket was either 3, 4 or 5. Fred's lawyers provide the following argument to support the claim. We have 2 alternative hypotheses. Either Fred won the lottery, that's H of F, or Jane won the lottery, H of J. We have the evidence E that the winning ticket was a number between 4 and 10. The probability of E, given the prosecution hypothesis, HF, is 2 over 3, because if Fred won, there's a 2 over 3 chance that the winning number was 4 or 5. The probability of evidence given the defence hypothesis, i.e. that Jane won, is 1 over 2, because if Jane won, then there's a 1 over 2 chance that the winning number was 6. Hence the likelihood ratio is 2 over 3 divided by 1 over 2, which is equal to 4 over 3. As the likelihood ratio is greater than 1, the evidence supports H of F, that Fred won the lottery. Now it turns out that while the evidence supports H of F over H over J, it doesn't support the hypothesis that Fred won. And that's because the correct defence hypothesis is not H of J, but rather not H of F. And that is the hypothesis that the winning ticket is 1, 2, 6, 7, 8, 9 or 10. The probability of the evidence given that correct defence hypothesis is 5 over 7. And hence the true likelihood ratio is 2 over 3 divided by 5 over 7, which is equal to 14 over 15. In fact, the probability of H of F drops from a prior of 0.3 to a posterior of 0.286 after getting the evidence. So the problem is caused by the prosecution cherry-picking an alternative defence hypothesis, which sounds reasonable, but is not the negation of the prosecution hypothesis. And similarly, here's an example that proves that if the hypotheses are not mutually exclusive and exhaustive, then we can have evidence with a likelihood ratio that's equal to 1 that's still probative. And in this case, it's the defence rather than the prosecution, which is cherry-picking the alternative hypothesis, that causes the problem. And this is something that you can read up at your leisure rather than me go through it in detail now. Now, in case you think that examples like that are unrealistic, I can tell you that essentially the same error is made in every case of DNA evidence. What the forensic expert actually uses is the prosecution hypothesis that the DNA belongs to the defendant and the defence hypothesis that the DNA belongs to a person unrelated to the defendant. That's because it's much easier to estimate the necessary probabilities with that assumption. And these hypotheses are not mutually exclusive and exhaustive. So if, for example, the DNA belonging to the defendant's twin brother is a credible possibility, then a very high likelihood ratio does not imply a significant increase in the probability of the prosecution hypothesis. And conversely, if the defense hypothesis is that DNA belongs to the defendant's twin brother, then the likelihood ratio here is equal to 1, but without credible evidence for this defense hypothesis, the DNA evidence is still highly probative in favour of the prosecution hypothesis. And things are even worse in practice for mixed DNA evidence, because the prosecution hypothesis is typically the suspect and one unknown unrelated person are included in the DNA mixture. And the defence hypothesis is that the DNA comes from two unknown unrelated persons, both unrelated to the defendant. Now, these hypotheses are not mutually exclusive and exhaustive. We can't be certain about the number of people in the mixture and the extent to which they may be related to the suspect. Now, while some people are aware of the problem of using a likelihood ratio for non-exhaustive hypotheses, very few people are aware that in practice the likelihood ratio is rarely calculated properly, even if exhaustive hypotheses are used. And this is because the only situation in which the likelihood ratio is easy to calculate is where you assume that there's a single hypothesis and a single piece of evidence. And in practice, this is never true. Even the apparently simplest examples involve multiple related hypotheses and pieces of evidence, and calculating the correct likelihood ratio for the value of the combined evidence on any particular hypothesis can't be done without using what's called Bayesian network inference. And so what happens is that the forensic experts try to force a complex multi-node graphical problem into a two-node graph like this. So for example, what is generally assumed to be the model to calculate the likelihood ratio for DNA match evidence involves just a single hypothesis and a single piece of evidence. But in practice, there's no direct link between the hypothesis here and the evidence here. And in fact, there are all these multiple unknown hypotheses in between. And it's not just the potential for errors being introduced with the crime scene sample, you also have all of these potential errors with the reference sample. Now the point is you need to know all of the local conditional probabilities in the whole model, and there's no way of calculating the correct likelihood ratio for this model without the full Bayesian network inference. And that work is covered in this recent paper. The final issue is one which I've already touched on, and it was demonstrated in the reference paper, which is that a high likelihood ratio for a mixed profile match is completely different to a high likelihood ratio for a single profile match. And that point really is not well understood. A likelihood ratio of 1 billion for a single profile match must lead to a high posterior probability supporting the prosecution hypothesis if done properly. However, a likelihood ratio of 1 billion for a mixed profile match still means that the posterior probability that the person is a contributor is theoretically very low, even if we have mutually exclusive and exhaustive hypotheses. And to highlight some of the problems in practice, here's the sample output from a probabilistic genotyping software. And there are a few things to consider here. So first of all, the highlighted rows indicate what are called a void at each of these loci. And these are instances where the suspect's genotype is not even included in the mixture profile. So one of his alleles is there, 25, but the other one is not. Now the point is that probabilistic genotyping analysis takes full account of the peak heights of each allele in the mixture and the possibility of drop out and drop in. So that, for example, the probability that the allele 13 is missing at that locus due to dropout is incorporated. The idea that there's such a high likelihood ratio supporting inclusion is highly counterintuitive, given the fact that there were 3 loci at which the suspect's genotypes were not detected. Now, on top of this problem, the analysis and conclusions are misleading, even if we accept the multiple assumptions made for the statistical analysis and assume that the DNA was processed without errors. So, for example, we can't be certain there are 4 contributors, and with the increasing use of low template DNA, the uncertainty about the number of contributors massively increases. And the likelihood ratio appears to be a statement about mutually exclusive and exhaustive prosecution defence hypotheses, but that's not, we know, how the likelihood ratio is calculated. And the summary conclusion is certainly not true when all uncertainty is considered. So what the experts should have concluded is something like this. So all of what I've said so far provides ammunition for challenging inappropriate forensic likelihood ratios generally used by prosecutors. But although it's tempting to dismiss any discussion of the prior, in practice there are priors that can be used which can destroy the defence arguments against the likelihood ratio, even when it's used incorrectly. So first, whether we like it or not, people, whether they're the police, the lawyers or jurors, form their own subjective priors. There's nothing wrong with having very different priors. Bayes enables you to determine the full range for the posterior probability given the different priors, and that's something that should be welcomed. Second, we've done work that we believe makes it possible to come up with what we call the opportunity prior that provides an objective prior for a large class of crimes. So assume a crime has taken place and that it was committed by one person against one other person, e.g. murder, assault, robbery. Then the crime scene is the smallest physical area in which it's certain that the crime happened. And the crime time is the smallest time interval between which it's certain that the crime took place. Now imagine we can observe people who are in the crime scene at any time during the crime interval. Now we generally don't know who was at the crime scene during the crime interval, but it's possible to estimate the number of people n, other than the victim, who were. And by definition, the criminal is one of these n people. If we know that the suspect was at the crime scene during the crime interval, then the truly fair prior probability of guilt is 1 over n. And that's as close to innocent until proven guilty as possible. Now we can also incidentally handle the case where the suspect was not at the crime scene during the crime interval by using the notion of an extended crime scene. So suppose that a mixed DNA profile of blood is found at a crime scene, and the prosecution claims that the suspect's DNA is in the mixture with a very high likelihood ratio. Now, as we've seen, in the absence of other evidence, this is essentially meaningless. But if the suspect was known to have been one of at most 100 people who were at the crime scene, then even taking account of all of the potential errors in the likelihood ratio calculation, that opportunity prior of 1 over 100 generally leads to a high posterior probability that the suspect's DNA was in the mixture. And here's the paper that discusses the opportunity prior. So in conclusion, in most practical cases, the use of the likelihood ratio for DNA evidence is highly misleading or simply wrong. And that's because the likelihood ratio generally is based on hypotheses that are not mutually exclusive and exhaustive, and hence don't provide a measure of probative value of the evidence. It fails to incorporate the impact of multiple relevant hypotheses and evidence, especially about potential errors during the DNA collection and analysis process, and only a full Bayesian network inference can calculate the correct likelihood ratio in such cases. We've seen that the problems are especially acute for mixed DNA evidence. Even if calculated correctly using mutually exclusive and exhaustive hypotheses, interpretation of the likelihood ratio still requires assumptions about the prior probability. However, it's extremely dangerous from a defence perspective to rely on this weakness of the likelihood ratio, because in many situations a reasonable opportunity prior can be determined and generally will be informally considered by jury members.